So this is section 11.2. This is continuing with quadratic reciprocity. So what this section does really is sort of introduces the law of quadratic reciprocity and does a few calculation examples. So just for sort of a brief intro here. So the law of quadratic reciprocity establishes a connection between taking two primes, p and q, and establishes a connection between when p is a quadratic residue mod q and when q is a quadratic residue mod p. Right? So we'll say the law, which is this theorem is called the law of quadratic reciprocity. This establishes a connection between these two questions. Is p a quadratic residue? Mod q, and is q a quadratic residue mod p? And this is where p and q are odd primes. So I'm not going to prove this theorem. The proof is fairly lengthy. It has some lemmas that are also fairly lengthy, so it takes some time. But what I do want to do is sort of give the theorem. So I'm going to abbreviate this LOQR for law of quadratic reciprocity. So what it says is the following. It says suppose that p and q are odd primes. So I'm going to state the way the theorem is formally given and then the way we'll actually use it. So it says if you take the product of the two Legendre symbols, so what you get is -1, that's a terrible looking one because it looks like a parentheses, -1 to the product of the powers p minus 1 over 2, q minus 1 over 2. Now, in practical terms, this is the same as saying the following, that p over q is the same, this is a case thing, is the same as q over p if either p is congruent to 1 mod 4 or q is congruent to 1 mod 4. And it's negative q over p if p is congruent to 3 mod 4 and q is congruent to 3 mod 4. So in other words, if either is congruent to 1, you could just flip it. And if both of them are congruent to 3, then you have to negate it when you flip it. So again, the proof of this is omitted because it's long. So what I just want to do for some calculations, call this part 3, is I want to couple this with a few other rules. So let's say coupled with the following. Let's compute some Legendre symbols. So with the following, I'm just going to put down a brief reminder of the things that we looked at, right? So in other words, so this is for calculating, let's say, a over p, when p is a prime. So the first thing is for simple values, trial and error. So b, if a is congruent to b mod m, then a over m equals b over m. So I'm going to call this reducing. I'm just making these names up to make it easier to reference as we go through. So for C, we had a rule that says AB over P equals A over P, B over P. I'm going to call this splitting. And then for D, we had a squared over p equals 1. I'm just going to call this the square rule. And then two other rules. We had E, that negative 1 over p, this is 1 if p is congruent to 1 mod 4, and is negative 1 if p is congruent to 3. Terrible looking 3. It's congruent to 3 mod 4. And then f 2 over p, this is 1 if p is congruent to 1 or 7 mod 8, and negative 1 if p is congruent to 3 or 5 mod 8. So take all these facts. I'm about to erase the screen to sort of make some space for doing calculations, but make sure these are handy, right? So let me circle them all just so we're clear that this is reciprocity. This says that you can basically flip your Legendre symbol over as long as you negate it if you need to, right? So you only need to negate it if both of the primes are congruent to 3 mod 4. Otherwise, if either of them is congruent to 1, you can flip it without negating. Then trial and error for small values. So what I mean by that is, for example, if you're doing, say, 2 over 5, and you want to know if 2 is a quadratic residue mod 5, you could just square everything mod 5 and see if you get 2. And if you do, you're good, and if you don't, then you don't, right? So reducing just basically means, I called it reducing because typically we're using this to reduce the numerator mod the denominator. Splitting what you use to divide things up, to simplify the problems. The square rule we'll just use whenever we have a square in the numerator. You could just have 1, that's it. And then E and F, these are special cases of what you can do, what we can do if we're calculating 2 over p or negative 1 over p. So make sure you have those handy. So I'm going to call these two last ones just for reference. I'll give them some names. I'll call this the negative 1 rule right here, and I'll call this the 2 rule. That way I can just say it and make the justification really easy. So let's just work through a couple of examples, see how this all works. And that's all we need to do. So take a look. First example, what we want to calculate, let's calculate 48 over 29. So we're either going to get plus or minus 1, and what we're determining here is whether or not 48 is a quadratic residue mod 29. In other words, is it a perfect square? So we'll go through this step by step and see what's up. Right? So first, 48 over 29. The first thing we notice is that the numerator is bigger than the denominator, so I can reduce it. So I'm going to reduce 48 mod 29, and we get 19. This is by reducing. And I'll justify this is because 48 is congruent to 19 mod 29. It's because 19 plus 29 is 48. So second thing, now that these are both primes, we can use quadratic reciprocity, and I can flip this, and I don't need a 19. Remember, I don't need a negative. Remember, we only need a negative if both of them are congruent to 3 mod 4. In this case, 29 is congruent to 1 mod 4. So this is by the law of quadratic reciprocity. So now that I flipped it, the reason we flip it is I can reduce again. So this is 10 over 19. This is reducing because 29 is congruent to 10 mod 19. So now what I can do, I can't flip it again, right? 10 is not prime, so I can't use quadratic reciprocity yet, but I can split. So now what we'll do is we'll do them independently. All right, we'll look at these separately. So let's call this A. I'll call this B. Because for A, we can use the 2 rule. So we get 2 over 19. So remember what the 2 rule says. 2 rule says we check whether the prime 19 is congruent to 1 or 3 or 5 or 7 mod 8. So this is equal to -1 by the 2 rule, because 19 in this case, if we look mod 8, this is 3 mod 8. So then we know what that is. So now look at B. So now B, because 5 and 19 are both prime, I can use quadratic reciprocity again, right? So B is going to take a few steps, right? So we get 5 over 19. So we notice that 5 is congruent to 1 mod 4. So this is 19 over 5 by the law of quadratic reciprocity, because 5 is congruent to 1 mod 4. So we're continuing with B. So then we reduce again. All right, we reduce mod 5. This is my reducing, because 19 is congruent to 4 mod 5. Right? And then since 4 is a perfect square, this is 1. So if we go back and we look at what we did, let me circle some things here. Right. This thing that we originally wanted to calculate will turn into this product. The first of those is -1. The second of those becomes 1. So at the end of the day, we can say that 48 over 29 is -1 times 1, which is 1. Oh, sorry, which is -1. So we conclude 48 is not, or let's say it correctly, 48 is a quadratic non-residue mod 29. It is not a perfect square. In other words, x squared is congruent to 48 mod 29, has no solution. So all we're doing here is we're using those rules in various ways. So let me do one more, and this next one will actually be even quicker. These things actually really work pretty fast. So for example, let's calculate (105 over 1009). Now, for what it's worth, keep in mind that 105 is not prime, so it's very tempting when you see two odd numbers to use quadratic reciprocity, but we can't. So note that 105 is not prime. So no law of quadratic reciprocity yet. So what do? Well, we can split it up. All right, so 105 is 3 times 5 times 7. This is because, just so we're clear, because 105 is 3 times 5 times 7. Now, each of these, right, I'll label them ABC, but they go by pretty quick. Right, each of these, the numerator is a prime, so we can use quadratic reciprocity. Right, so So in this case, 1009 is a prime, it turns out. You can check that if you like. So 1009 is congruent to 1 mod 4. So this is 1009 over 3. This is law of quadratic reciprocity, because 1009 is congruent to 1 mod 4. Now we can keep going with this. So we can treat this like a little algebraic equation. So what we can do is we can reduce it. This is reducing, because 1009, there's a little bit of work in here, right? This is congruent to 1 mod 3. We're reducing the numerator mod the denominator. And that's equal to 1 by the square rule. So for B, we look at 5 over 1009. This is 1009 over 5. Again, law of quadratic reciprocity. Same reason, because 1009 is congruent to 1 mod 4. Then we reduce. This is reducing, because 1009 is congruent to 4 mod 5. And this is 1 by the square rule. And then for C, 7 over 1009. Again, quadratic reciprocity. And we reduce it. So what's out? We reduce 1009 mod 7, we get 1. And this is equal to 1 by the square rule. So when we put it all together, 105 over 1009 is 1 times 1 times 1, which is 1. So we conclude that 105 is a quadratic residue mod 1009. In other words, it is a perfect square. So if you prefer, x squared is congruent to 105 mod 1009. Let's say has a solution. And that's it. That is the end of the section. It's a pretty quick section because most of the section is tied up with proving the law of quadratic reciprocity, which we're skipping. So we'll call it a day for that.